So it's recording. Okay, hi everyone. Thank you all for coming to our first actual workshop. And also good to GM if you can make it. So yeah, today we're going to be talking about an introduction to distributed systems. We're going to cover like fundamentals, and then get you guys all set up with the project to develop them. All right. So before we do that, this is like the ACM portal code. We had it at the end of our slides last time, but we didn't quite get there yet. So yeah, if you want to do that point thing, this is the code to do it. We'll just give you like a minute or so. I don't know. They say you can like win money or something, but I don't know.
Are we doing a freshman year?
Okay. All right, I think we're good. We good to move on? Any objections?
All right. So we're just gonna do a quick recap of what cloud computing is. If you went to the GM last week, this should sound familiar, but yeah, we're just gonna go through it real quick. So why should I care about the cloud? So if you look at this line has been going up. It is very big, and that means a lot of the total server compute is in the cloud. It's outsourced to cloud computing companies, and it's only been growing over the past decade. If we look at cloud adoption for enterprises, 76% is from AWS, and some of them also use Azure, GCP, Oracle, VMware. All that, all very, very big. A lot of companies use these cloud computing services. And look, the revenue, it's been going up, which means Jeffrey Bezos is very rich now. Okay. And then, yeah, so why cloud computing? It makes it much easier to create applications that use distributed systems. You have a lot more, you have less control, but a lot more standardized interfaces, which allows you to iterate very fast. Yeah, one thing though, the AWS costs scale exponentially. So if you hit your startup on AWS, Jeffrey's coming after your money. So there we go. Yeah, so we have an on-premise model. It's a lot of upfront costs. You're gonna have to. It's very inflexible. So if you want to increase your server's capacity, you have to like physically find space for that. And if you don't have space for that, you have to build a new building, and just things like that. A pay-as-you-go model allows you to only pay for compute that you actually use. You have much more reliability with your hardware because if a server breaks or something, the engineers at Amazon are going to probably figure that out, and you can request a lot more storage or a lot more compute within minutes. You don't have to do all that fiddling around with your servers and stuff. They have like virtualization, in their interfaces, like to request more resources. Yeah. Okay, so now is the new stuff. So what exactly is a distributed system? So a distributed system is made up of three things. Wait. Yeah, no, it's made up of one thing connected together. So a node is a device or software process, and these don't actually have to be located on different physical devices. Like you can have many nodes running on a single physical server. But yeah, this is just a logical way of splitting up your application. So a key problem is how do we allow many nodes to collaborate so that it's more powerful? Now, we'll get into that later on, but like the central issue that distributed systems are supposed to solve is that from the user's perspective, system should only appear identical as if it was running on a single local machine, which means that all the synchronization issues, all the network message passing, all that should be invisible to the end user. Okay.
You minimize this thing also.
Okay, I'll minimize that. Okay, like that. Okay, so what exactly is a node? A node is an autonomous computing unit. So with this, since they're autonomous, there's going to be problems with synchronization because on a physical machine, when you do say write this value to a register, you know that only one of those instructions can happen at a single time. However, there's no guarantee of atomicity for your operations when you're using a lot of autonomous Unix, right? You can have one message go to you can send like multiple messages, and then they can come back different values, from like different nodes. And so we don't have like a global clock or anything on a CPU as we in a distributed system. There's also an idea of groups, which means that which nodes are connected to each other and how does a different node enter a group. And this is really good for like splitting up nodes by what purpose they serve, what permissions they have, things like that. And so an open node just means that anyone can join the group, and a closed group just means that there's some process that has to happen to authenticate each node before it's allowed to properly operate. And also we have a structured group, which means that for example, a binary tree, right? That's example of a structured group. That it means that the topology of your nodes has to follow a very specific set of rules, versus unstructured, which means that you can have pretty much any graph topology mapping between your nodes. There's no really guarantee of any type of structure. And so again, single coherent system, all of this has to be hidden from the users to provide what's called transparency. Okay. And then so this is an example of BitTorrent. We see that BitTorrent stores a lot of files across the nodes into a swarm. And then basically what happens is that when you request a file, you basically just get a bunch of metadata to see like where each portion of your file is stored, and you would contact each of the nodes to get that tight slice of the file. Yeah, it's an example of an open group membership. So like anyone can join the BitTorrent network, and if you join, you have to actually also act like both as a customer, as a user, and as a server, since you cannot use BitTorrent without serving files to other users, which is part of the really core technical innovation of BitTorrent. It solves the free riding problem. We'll get into that later, but yeah. Okay, so what exactly is a middleware? A middleware for a distributed system is analogous to the operating system for a local system. So what does this really mean? Well, in an operating system, we have system calls, which basically wraps up a lot of these cumbersome, hardware-specific operations inside a single function call, which we can just use that instead of having to worry about, okay, what does the Intel architecture do? What does ARM do? What does RISC do? All that it's taken care of. All that functionality is taken care of by whatever operating system you're using. So a middleware also builds on top of that. So the core functionality of middleware is that it provides resource distribution across a network. So what does that mean? It means that if you want to access a resource from another node, or maybe that resource is split across many nodes, you shouldn't have to care about that. The middleware takes care of that for you. And so all you have to do is say to the middleware, hey, get me this resource, and it just returns it for you without you having to worry about it at all. And so this is what's called that's what's called transparency. In addition, middleware also provides communication. So like a message passing, what format are you passing the message through? TCP, UDP, maybe custom networking protocol that you made, all that. It also provides security, accounting, and fault tolerance. So when something goes wrong, maybe the transaction didn't complete correctly, the middleware would take care of that and either retry that transaction or just return an error or whatever. And so some common services, like not all of these are necessarily provided by a single middleware. You might have to layer a lot of them together. The common services are the communication. So an RPC interface like gRPC would be an example, I think, maybe, or maybe it's like a gray area, not technically a middleware, but something similar to that. Transactions. So this would basically mean that if I call a function on a distributed system, it ensures that that transaction can only be completed one at a time. So if multiple other users call that same function, there won't be any sort of errors due to synchronization. in composition basically allows you to integrate other people's distributed systems into yours. So for example, like the APIs, like in Google Maps, like Google created this global mapping software. And now we can use that in our own apps, which is technically an example of a middleware. And also reliability. So you can pretty much do some certain guarantees for your applications, which is good for some reason. But yeah. Okay. And so this is an example of a middleware. So here we see that we have many different applications running on different physical machines. And each of these physical machines is running an operating system. It doesn't matter which one, as long as it's compatible with middleware, things should work just fine. And then this communication system is just how these physical machines are linked together. So like you're pretty much how are they connected to the network. And when one application calls a standardized API, that gets translated into the middleware. The middleware handles the communication and all the coordination between all these physical nodes, and then returns that data to that application. Okay, so designing distributed systems. Okay, so what is our goal in designing a distributed system? The four main things we need to think about is one, resource sharing. That's the entire point of distributed systems. We want to access the resources stored on many different physical devices. We also want transparency, right? That's basically, as I said before, you want to treat your distributed system as a local, as pretty much the same as a local system. So if you call a function, even if it's handled in a distributed manner, you shouldn't have to care about that. And the interface should also be open. So like, if other people want to use it, it should be very easy to access that. Or if you want to keep it closed, it should be like really well documented. The standards should be standardized with like some international organization or something to keep it very simple to change and stuff. And it should also be scalable. So if you want to like add more components to your system, it should not have to have it should not be that difficult to either scale up or scale down. Okay, so let's go into the first one. So resource sharing. There are many different types of services. For example, file storage, right? You store a bunch of files across your network and you want to access them, just from your local machine. For example, your Windows is network file system. If you see the green pipe, that's an example of file storage. Your CDNs, Cloudflare does this. Basically, they distribute static content from a master node all the way to a bunch of servers across the world, so that users can access endpoint that's much closer to them than having to go through like many different continents and then accessing your singular laying server that you store your web page on. And then scalable servers. So that's basically like you deploy an application, and then maybe like the load on your server is very irregular. So you get a service that auto scales up and down depending on the network traffic, depending on the load on your system. And so we want to make it very easy for users to access these remote resources. And so one thing we need to think about is storage facilities, right? All of these, even though it's like the cloud, we think of it as a black box. We need to think about like, where are they located physically, right? Because that matters due to, like network traffic, latency, how many servers do you even have? How are you going to take care of the water, electricity, your cooling, all that? Hardware as well. Like maybe there's a natural disaster, and it takes out part of your server, and boom, everyone's data is gone. That's not very good. Also data files, services, all that. So an example of a distributed system is the internet, right? It's the largest distributed system in the world. Basically, all of these web pages are hooked together through open standards, and you can pretty much access any web page by sending a uniform HTTP protocol message to some random server. It could be a CDN. It could be a actual server owned by the company that runs it. Whatever. and it all fits together seamlessly, so you don't have to care about any of this at all. Okay, yeah, and this is just an example of CDN. So here, let's say I have a website and I have like my main master server. I would basically just send copies of the website to the CDN, which has physical servers all across the world. And then when people want to access it, instead of having to go into my main server over there, they can just access a CDN that's like much closer, and it would be much faster to get to load my web page. Okay, and a quiz time. Wait, should we have put a QR code?
Oh, maybe.
You still want to use it?
How much space?
I forgot it. Wait, shit.
Does it wait properly?
Oh, thank you, does. Wait.
Okay, we'll skip over the quiz.
Okay.
You guys go in there.
Wait, how do I
Yes.
go back?
You guys have any questions on the stuff that we've done so far? Then?
There's like, no, everyone's good. Yeah. Not necessarily. You would have to like use typically how you do it is like you make a chain, but because you have like the development branches and like actual production. So like if you want to push it to production, you have to put it to your like main server, and then that would like propagate to the CDS. So yeah, it would be like typically be like a manual thing, since if you mess up, it's like website's down.
Yeah, I'll also say that sometimes the CDNs will like they have some sort of caching where like even if you push it out, the CDN itself will have the stale version for like a short period of time, and then periodically it will pull from wherever the main source is.
So yeah, it's not nothing definite, but yeah, depending on like what you prefer. So yeah, transparency. Okay, so there are 7 different types of transparency. The first one is access transparency. And these are basically to hide the differences in underlying machine architectures. So, for example, if I wanted to access a website, the way I would do that is enter a URL. That's an example of access transparency. It means that I have a standardized way to access these resources, regardless of what tech stack the server is running, what underlying operating system the web server is built on top of, things like that. The next one is location, right? So if I want to access a resource, I don't have to care about its actual physical location. So one example of this is, like an IP address, right? Like I don't have to say, go to this, server over here, right? That simple IP address, I can access that through anywhere in the world, regardless of if that server moves from like USA to Canada. It really doesn't matter to me. Okay, next. The relocation means that if I move resources from like this server, from like one server to another server, the end user should not have to care about that. So, for example, if I use Google Drive, maybe Google changes the location of my files from like from being in Utah to like New York, right? But when I go to Google Drive and click on that icon, it still pops up, right? That file is still there, and I did not even know this happened. So that's an example of relocation. And so migration is more of like a niche type, but it's basically like if I move while I'm connected to the system, like it should not be affected, right? So like for example, if I use a cell phone, I can move around, I can do whatever. But the end user on the other end does not know what's happening here, like physically. It maintains connection regardless of my mobility. And so replication, we've gone over this just before. So CDNs are example. So if I have like maybe caches of old resources, or like backups or copies, the end user should not be aware of that at all. And concurrency. So all the resources should be kept in a consistent state, and this is kind of related to the atomicity principle as well. If you don't handle the synchronization, you can have like one server with one copy be of your resources be different from another server with a different copy, and they both received a request to perform some action on your data, and then now they're in a different state, and you have no way to resolve that conflict. So you got to keep your entire system in a single unified state. And then failure. For example, DNS. If my DNS request fails, um, you know, it will retry with a different DNS server. And so that's an example of masking your failures, just like I do on my resume. So yeah. Okay. Yeah. Okay. Okay. Next is open. So we want an open standard for our distributed system. So it should be very clear how our services and components work. One example of an open standard is an IDL, right? So an IDL is basically allows processes with different service implementations to behave in the exact same way. And so this basically allows you to operate with maybe a different vendor, if they use the same interface, right? And so something I want to make clear is that an IDL is not like a pronoun, right? It's not like you would say like, oh, Python or C++. It would be more similar to saying like Python programming language, in the same way that it's like maybe you have X IDL, that would be a specific thing, but an IDL is just something that serves that is a general term, basically. And extensibility. So if I want to build new components and integrate them into my system, it should be very easy to add new components as well as fix existing ones. And this is all basically like how well have I designed my system and how well have I documented it. Oh, okay. Yeah. So yeah.
I have a question for the transparency side.
Yeah.
Wait, what is transparency like itself? Because I feel like that's like not transparency. It's like you're hiding physical location.
Yeah, no, hiding it is okay. Yeah, so transparent basically has like an opposite definition within computing. Like, for example, in an operating system, we call it things like transparent. If you can basically just not care about what's happening underneath, right? So if I have USB and I plug that into my computer, it doesn't matter which vendor I use, right? I can still access that data, and I can even like swap out my hardware components. Maybe I want a different CPU or something, but it will still run the same, right? So that's what we mean by transparent. It means that the underlying issues are not affecting me, right? I can just still use it in the exact same way, regardless of what changes happen underneath. Right, and so this is an example of an IDL. So over here we have this OMG IDL, which is very similar to like C++ syntax, and over here is Microsoft IDL, which is growth because it's Microsoft. Okay. Okay, next. Yeah, so this is an example of how an IDL would work. So over here we have a C++ implementation. We have a Rust implementation, we have a Go implementation, and then we basically download like an IDL file, which basically defines like, okay, here are all the things you can do, with this interface, right? You can say like, oh yeah, here's this function, here's what it should do, this is another function, and then we actually bind an implementation to that. So this IDL will translate the data coming through our network, and then convert that and just call whatever function we bound the interface to, regardless of what the actual programming implementation. Okay. And then scalability. All right, so how do we make our system more robust over time? And so you want to add more resources and users without greatly impacting performance. In addition, geography makes a big impact on the performance of our system, right? So the actual physical length of the cables can greatly affect latency, And how do we manage our system too? Like administration, sysadmins, maybe we handle, have one nation, have one another nation. That's pretty much easy setup. We could have also international organization, but yeah, it's basically up to you how to do that. And so we have something called a computational grid, which is basically a distributed system of distributed systems. Second, we'll go over that later on. But yeah, it's just really common in like academic settings. A lot of universities do something similar to this. And we also have safeguards to make sure that your components cannot be tampered with. Users are within the computational grid. They are trusted and verified. And this is usually not automated. It has like some human aspect to that, but you have to like meet them and check off. Okay, and you want to take it.
Sure. So like what are the actual approaches that we take to scale? So yeah, one of the main things that we're trying to do is to like hide the latency, right? We really want to cut that down. That's the whole one of the main reasons why we actually try to scale. So yeah, things that we can do that would be making asynchronous communication calls. So really that just means we're basically making a call and then continuing with some other work in the meantime, waiting to go back. And then we can partition our data. So instead of having all of our data in like one large data store that we have to kind of parse the entire thing, if we want to find a particular record or something like that, we can divide it across multiple nodes and then have each node kind of look for whatever record we want. That way we can kind of split up the work. And then replication also helps. So this is where we kind of redundantly store like whatever content we want. So for example, with like a CDN, where we're storing our website in multiple servers across the world, so that users in like Asia can access their own kind of local server, and us in America, we can access our own kind of. Okay, cool. So before we get into types of distributed systems, which will more or less apply the stuff that we talked about before, any questions on how distributed systems are designed, like considerations? Okay, cool. Yeah, you can see. Yeah. Okay. So yeah, I have a list of the types here. We're basically going to kind of go through a scenario where we illustrate when each of these types are applicable. But just to quickly introduce them, we have high performance computing, which contains cluster computing and grid computing. And then cloud computing kind of has a unique place in there. So we'll talk about that. And then we have distributed information systems and pervasive systems. Okay, cool. So we're going to kind of walk through the scenario of creating a new company. So yeah, the name I made these slides a while ago, but I was like when Facebook changing its name. But yeah, we're going to be going with Beta, and we're going to set up an office in LA. Unfortunately, our site is a big hit. So what might you guys think could be a possible issue that could occur if our site is really popular? Yep, go ahead. Okay. What might be yeah, good answer. What are possible reasons that it could crash? Yeah, right. Oh, sorry.
Maybe if you have one node, that single node can't handle multiple requests from like multiple users.
Yep, that's a good answer. Does anyone else have any other ideas? Why could it possibly crash? Yeah, I mean that was the answer of the book. It's a good one. Yep, good. Okay, so this is like an error that you'd probably see if it's overloaded. Okay, so yeah, how might we go about solving this overload? I threw up a couple images on here as a hint, but it's a little bit obscure. So yeah, go ahead.
So you can either make your system like bigger, like you make each unit bigger, or you have.
Yeah, exactly. Yeah. Keep going one more time. Okay. Oh, okay. Yeah, that's good. Neither one is good. Okay, so yeah, basically, you're exactly right. We can either scale up directly, like a single node. So this is known as vertical scaling, or we can kind of add additional nodes, which is known as horizontal scaling, where we're trying to run things in parallel. So generally with the distributed system, you want to go with horizontal scaling in most cases. There's certain cases where you'd want to scale up vertically. Okay, cool. Yeah, and this is just a diagram. Any questions on that so far before we move on? Yeah, go ahead.
Can you go over the difference between vertical and horizontal scaling?
Yeah, sure. So like if you take a look at this image here, horizontal scaling is basically adding additional nodes. So basically, instead of sending all of our work to one big server, we're sending it to like 5 servers and we're doing it in parallel. And then vertical scaling is when we basically increase the CPU or RAM of like a single. Yeah.
Okay. Thank you.
Any other questions? Yeah, good.
So, like, I feel like horizontal scaling is like mostly like a better option.
Yep, yeah,
It's
right.
like more balancing, but like in that case, I would assume vertical scaling is like how much compute versus total for horizontal is more cost effective.
I think it kind of depends on like the workload. From what I've seen, if you're running it on the cloud, horizontal scaling will be a little cheaper than vertical scaling. But it depends again, also depends on like what kind of tier you're at. If you're at like if you're scaling up and you're already like scaled up quite a bit, then it's just scale up, it's gonna be more
Yeah,
expensive, I
like
guess.
if your workload can be completed in parallel, you usually want to go with horizontal scaling. But if it requires a lot of cross node communications, that'll run up your AWS costs a lot. And so in those cases, you might want to keep it all in a single machine, so like you have access to all your resources you need, to minimize the network costs, and also that can decrease latency too. So yeah.
Well, yeah, good question. Okay, so um, yeah, you can go on. Okay, great. So now we've basically run with that, right? We're going horizontal scaling. So if we look at our diagram here, we can see we have some sort of node up there, and then we have 3 servers in parallel, and then we have some sort of database here. So yeah, basically the idea is to do what's known as load balancing, where we just like get all of our requests and then we distribute them to our servers. And the idea is our servers will be more or less balanced so that our workloads are also more or less balanced, and we can successfully address everyone's requests. So this is a prime example of cluster computing, where we're basically we have a series of nodes, right, or each of our kind of servers here, and we're distributing work among them and running it in parallel to kind of satisfy the requests as they come in. So yeah, it seems to be working great. But what might be some possible issues that could result from having this LA office set up like this? Emphasis on the LA office. Yeah, go ahead.
You like run out of space.
Yeah, that could definitely be a real concern. So like in a single office, right, like you only have so much physical space. Anything else? Yeah, go ahead. Yeah, that's another great concern, right? Because we don't have a lot of critical redundancy here. We just have one location. So that's yeah. How might we mitigate that? How could we fix that?
Yeah, like availability.
Sure. Yeah, we basically open our office somewhere else. Okay, so just hold that thought. Yeah, go on with that. Okay, so yeah, for cluster computing, let's quickly talk through some of the advantages and disadvantages, because this is like basically the key type of distributed system that we're going to be working with. So we have high performance because all the nodes are like either physically sitting right next to each other or have like a kind of high speed network that they're connected on. So it's like transparent and it looks like that. We have high scalability, at least if we're using at least if we can kind of physically add additional servers. We'll get back to that a little bit in a bit. We have high availability because different users can access it without any issues. And then we have relatively easy management because it's all in one location, right? We can physically walk there and like configure our server as we need to. And then disadvantages. So if you go back to slide, we can see that there's actually a bottleneck here, right? Because like everything has to hit this load balancer. So we still kind of have an overloaded node, so to speak. It's not doing a whole lot of work, but it still can be overloaded. And then in our current situation, we have to maintain our hardware ourselves. And it's relatively cost ineffective because we have to rent that space, like kind of pre-plan the hardware that we need, set it up, maintain it, that's it. Okay, so yeah, we just kind of discussed this. So yeah, one more time again. Okay, so yeah, the solution to kind of all of these problems that we noticed in with cluster computing, is to basically open a new office. So in our case, we've done so in a different country, so that we can kind of have even higher availability and different people can access our server or access our content even faster. So yeah, this is an example of grid computing, which Daniel mentioned before. Basically, the fundamental idea here is that we have a system of distributed systems. So like we have like its own kind of London office that's its own cluster computing distributed system, and then we have one in LA as well. But they're also connected directly together and can kind of communicate and address security issues, that kind of thing. Yeah, so what do you guys think are some of the advantages of going with this approach and disadvantages versus, I guess, just like the cluster computing approach? Yes, go ahead.
Based on the disadvantages of the cluster computing, there isn't like one node taking all the requests. It's being distributed among two. And if one sort of office like breaks down, the server goes down, still another office.
Yeah, great. That's a pretty strong advantage. Do you have something?
So I have a question.
Yeah.
So, like, would requests be like with between two, or would they normally go to the cluster one and then only go to the other one if it's the being overloaded?
Yeah, so it just depends on like how specifically they do, I guess, the DNS routing. More than likely it'll go to the cluster. That is the short answer. It just depends on like which, like how the network is configured. Yeah.
Is the data distributed between like the servers in both the offices, or is it just like one not into the time?
Yeah, I'm glad you brought that up. We're gonna talk about it. So yeah, just hold that thought. Yeah, what were you gonna say?
If the LA office goes down, people in LA will get rerouted to the London office.
More, I mean, this is a hypothetical scenario, but more than likely, like in real life, if you had two servers like this, it can be configured to do that. Yeah. Okay, you can move forward. So yeah, the advantage. Oh, did you have something you were gonna say?
Yeah, I was gonna say, can you like run like if you're making requests, and you needed like do multiple like operations, can you run them parallel between like if you view these two systems as two different distributed systems?
Yeah, so if you have like the IP address of the load balancers, you could definitely directly like choose which one you want to direct your request to. Or if you like an admin or something, you could definitely do that. From the perspective of if you'd want to do that, I think it may make sense unless you have like a really large like kind of global scale workload to just do it at one. Because that's already a distributed system, right? But yeah, it is possible. Sure. I mean, did you have a question? I mean, you were going to say something? No? Okay. So yeah, with grid computing, it's a little bit more flexible because we have multiple kind of distributed systems. We can choose how we want to balance work. We can choose like maybe one, maybe like the London office has to follow particular internet guidelines in Europe, but our LA office doesn't, right? So we can kind of configure it a little bit more granularly. And we can also connect disparate kind of organizations in this way. So for example, if we have like a bunch of hospitals and they all need some sort of like communication for like emergency scenarios or something, right? Even though they have their own network, their own distributed system, they can still connect in this manner. And then so the disadvantages are that because it's a little bit more like free form, the standards for it are kind of still evolving. And then you could run into some licensing and permissioning issues. And then again, connection issues, right? The whole idea behind this is to kind of do things quickly, right? That's the whole idea behind why we want a distributed system. But when you have distributed systems disparate across the globe, right, latency always is an issue, no matter how much we try to hide it. Okay. Any questions before we move on? Yeah.
What kind of license?
Yeah. So I think if you're trying to run like a particular piece of software, off the top of my head, I can't think of a great example, but I know like some software you have to run on your own hardware. Like you can't, like they won't let you run it on cloud, unless it's like private cloud, which is its own thing. But yeah, so I think with the scenario that would be a challenge that you could face. I guess you would face it in cluster computing because you're still using cloud. Okay. So yeah, basically the idea here is that since we own this LA office and this London office, we're running into kind of a high cost. So like we have to pay for the servers, the building, the databases, and like the technicians, any legal trouble that we run into, like maintaining the rents, whatever, right? So what would the cheaper alternative be to physically owning these locations? Yeah, exactly. Is that what you're gonna say? Yeah, so hopefully you filled it in now, by now. Yeah, cloud is just great. So here we're basically choosing to use AWS. So we're just kind of storing or using those servers in whatever region we choose, or availability zone, whatever. So yeah, the key idea here is that we have access to kind of virtualized servers, and virtualized like a database, I guess. So virtual nodes effectively, that we don't even have to maintain. It's all kind of abstracted for us. Yeah, well, it's like great, cheap, and it can run everything we need to run and scale very easily. Yeah, and another great thing is that it's a pay-as-you-go model. So we only really need to pay for what we use. So if we're not getting a lot of requests during a particular time, we can kind of scale down and then scale back up as the requests come in. Yeah, there are issues that we may run into if we're really, really large scale. But for most companies that are kind of like entering the market, like us in this scenario, it's not. Okay, so a little note on cloud computing before we go on. So there's a lot of text on this slide, but the essential idea that I want to communicate here is that cloud computing offers a couple of different, I guess, degrees of control over what you're running. So, for example, if we look here at the software as a service section, we can see companies that are offering software as a cloud service. So, like a good example of that would be like Gradescope. Gradescope enters in some sort of contract with our universities to kind of host, I guess, like problems, and then kind of if you upload something, it will store. It's actually built on AWS, but it'll store the file, underlying file. And I think recently they added some sort of like, if you submit code, it can like run it, like run tests against it and stuff. But the basic idea here is that they're offering a software service. So somebody buying the software as a service kind of service doesn't have to do any coding. They're effectively just buying some sort of software that they can integrate into their own platform. So a good example of that, like I said, Gradescope, is our university is buying Gradescope and then integrating it into Learn, whatever slide is called now. But yeah, so they're integrating some third-party software. So that actually is an example of cloud computing. Kind of a more traditional, something that you may think about would be this like platform as a service, where essentially you're able to use some sort of cloud computing platform to go in and configure some sort of, it may involve some code, it may be kind of through some sort of UI, but you're basically allocating resources that you can kind of use to create your own application. So some kind of key examples of that you may have heard about is like Firebase. That's effectively like a database engine, NoSQL database that you can configure through like through a UI. I think they also have a couple additional features, like you can run an app with it, that kind of thing. Elastic Beanstalk is another example where you can basically add some sort of like a Docker container or code or GitHub repository, and it will kind of do all the configuration for scaling, for like security, that kind of thing for you, and then allocate it and run it with a publicly accessible domain. So yeah, that's platform as a service. Any questions on those two before we move on to the last one? Okay. So yeah, and then the last one here is infrastructure as a service. So this is basically as close as you're going to get to having full control over the hardware, but still on the cloud, where like you can't walk into an AWS data center and like just press like turn off the server or anything, right? So these are basically like virtual machines. So something like Amazon Web Services EC2, where you effectively are running a computer that you can access through the terminal, like install what you want, leave what you want, like restart it, whatever. But you don't have like physical access to the machine. So if you want to like add more memory, you have to do it through AWS, and more than likely under the hood, it's going to kind of reallocate, like move over the server. We'll just like physically move it somewhere, but it'll be all kind of transparent to you. And then another example is like kind of cloud storage. So S3 is a good example of that, where basically you can kind of like upload files or do it for the command line. And it's effectively just a way to store files as if you were to kind of plug in a USB into a server and then upload the files. Okay, so yeah, any questions on that? On those three types of view? Okay, cool. So then, yeah, let's return back to that example that we were talking about, right? I'm going to step away slightly from cloud computing and more towards distributed systems again. So yeah, I like this dude at the front mentioned, good on you. We have a consistency issue here, right? We have two separate databases, or at least in this diagram, it looks like they're separate. So let's consider the scenario where I log into my account here in LA, and then I travel to London for some reason, and I try to log in. Like if my data is stored up here in this database, I'm not going to be able to access it when I'm connecting to the server, right? So how can you fix that? Yeah, good.
Maybe creating a distributed system of those two distributed systems.
Sure, that could be a way to do it. Effectively, what we want to do is make sure that these are the same, right? Or have at least some degree, some way to make sure that they should be the same. So, yeah. So effectively, what we're going to do is build a distributed information system. So we can kind of combine these two distinct databases into a distributed, I guess, database. So, yeah, basically, I've listed some of the goals here. These should match up with what Daniel was saying before. Right, we want our data to be consistent between our two database nodes. We want it to be reliable. So ideally, if one of them gets corrupted, we don't lose like all of our data. Right, we theoretically could have it stored somewhere else. We'll have some other way to recover it. We want it to be accessible from anywhere with like relatively kind of transparent speeds as much as the network will allow. And then we want our databases to be efficiently like storing data and performing whatever computations it needs to, so that we're not wasting money. Okay. So I guess kind of thinking about this a little bit more, like how we can actually go about building this distributed database, because this is kind of tied into the project a little bit. Let's kind of break down how we actually, like just at a single node, would store data in our database. Does anyone kind of, like there's some things on the slide, but like if I was to code it, what would I probably do to the right hand of the database? Kind of an abstract. The answer is on the slides. So to shout it out. Yeah, exactly. Thank you. Yeah, function calls is the way to go. Whenever you really want to do any operation, right, it's probably going to be some form of function call. So in this case, we probably have a file somewhere locally. Maybe we have the file contents in some buffer, and then we want to write it to our database, more than likely through some sort of function call. So we're going to say, hey, this is where my content is. This is where I want to store it. These are the credentials, and then send. So yeah, the advantages of this approach are that we can kind of hide the actual implementation of the function, right? So the function might be like writing it like to 10 different servers, or maybe just be writing it locally or somewhere, right? It doesn't really matter. Because we're like the design goal for us is to make it transparent, such that we can meet those other like 5 goals that we had in the previous slide. And then we can also hide any like retries that we have to do. So for example, if we're not able to contact the database at first, maybe we can kind of like wait for 5 seconds and then try again or something. We can kind of hide that all behind the implementation of that function call, so that users don't have to kind of worry about it. And then we can also reuse some of the implementations across different function calls that we have to make to the same database. Okay, yeah, any questions on that or move on? Okay, so we're going to delve a little deeper into that kind of solution to our problem. So yeah, the general way that this is implemented is either through a remote procedure call. So this is kind of what we were showing off at the GM, where we basically have 2 nodes and we're trying to communicate between them. So we have on our client, which in our case will be the server, which is a little ironic, but this node here that's trying to do the write makes a function call, but the implementation of the function is sitting over here, right? So it's kind of a remote procedure call is just another word for function. So it's basically a remote function, right? So it's calling the function and then sending the request over the network, and then kind of carrying out the implementation here, and then sending the response right back. Go back one last thing here. Yeah. So and then we can also have this. There's a notion of a remote method invocation. So this is basically where instead of just a function call, you have like a notion of a remote object on like the other node. So you can kind of perform operations on the object. And there's some sort of state maintained there, rather than just kind of function calls. We're not really going to delve into that too deep, but it's just something that's good to know. Okay. So yeah, before we move on, any questions on distributed information systems? Yeah, go ahead.
Can you reiterate again about the whole aspect of, yeah, like splitting functions?
Yeah, sure. So the idea is, so at this node, right, we know we want to write the data, but we don't know how to do that, how to do it, or where to save it, right? Because if we save it here, like at this server, then it's still not very useful, right? Because this server can't access it.
Yeah.
So we know we have to write it to this database. But the way that we do it is we have the implementation of the function sitting here, and the function call sitting here, basically the function header. So this is kind of like making use of like clients, like function stub, where we call the function, and then in reality, it will kind of communicate the request over the network, and then carry out the implementation here, and then send the response back. So we're basically splitting out the function across two nodes, but kind of doing it transparently. So like neither node knows that it's happening from a different node. Yeah. Good question. Anything else? Okay, cool. So yeah, let's quickly talk about ubiquitous computing systems. We're not going to get into this in this workshop really, but the idea behind this is that computers have become ubiquitous, right? Like a phone, your TV, your fridge, whatever, right? Everything is a computer to some extent. So there needs to be some sort of network between them and some sort of way for them to communicate, address any issues that they encounter. So the really big challenges that we encounter here are that because there's such diversity and maybe some of them move around, right? It's hard to kind of, and it's moving at such a fast rate. It's hard to kind of build a good system for it. But yeah, I think the key is to follow those design principles that we talked about, because that will allow the most people to contribute and the standards to emerge fast and efficient. Okay, so that was a lot kind of theory there. Again, I'll pause for questions really quick before we talk about network file systems and then go into the product. Okay, what time is it?
It's almost 6:07.
Okay.
Yeah.
Okay, so we're doing well. Yep, we can keep going. Okay, so what is a file system? We kind of went through the charade last time, it didn't go so well. So let's try to do it better this time. Okay, so I put something up there, right? File systems store digital files in an organized manner. Does somebody want to try to elaborate on what a file system is? Please. Yeah, so this image here should look familiar. If you have a Mac or PC or whatever, right? You should be able to kind of open up a file explorer and kind of navigate through some sort of like tree-like hierarchy where you can store folders and then files. Yeah, keep going. Keep going. Okay, so go back. So yeah, so these are the main kind of design goals that a file system would have. It needs to be hierarchical, meaning we can have different layers of a structure. More than likely, we're going to run into some permissioning issues. On cloud, this is a big thing because they have this principle of like least privilege, or I forget the exact name, but the idea is that you only give people the permissions they need, specific permissions they need to do a specific task. So like you probably want only particular users to have access to 1 and 2, and then everyone else to not have access to it. And then if you are duplicating files, maybe you want to be able to know whether that's allowed. So for example, if I have 2 files named stats.txt, can I have them in separate directories? Is that allowed? Can I have them in the same directory? Is that allowed? But can I have this folder with the name stats and then a file that's also named stats? So we have to consider all those edge cases. And then we may also need to consider the case of like, oh, so do we want this folder to be able to like loop back up here or something? It wouldn't really be a tree in that case. It wouldn't be a tree at all. But that's something that we need to consider when we're designing a file system. Okay. So yeah, just skip through, just note all the bullet points in. So yeah, talking quickly about the actual implementation of the network file system. This is going to kind of more or less model what are like kind of skeleton of the project models. Yeah, so this may look a little daunting at first, but in reality, it's not too tricky. So for each file, the key things that we need to store are the file contents, right? So whatever the like user is writing to the file, and then some metadata about the file. So this is probably going to be like the size, maybe where it's stored, maybe like the last time it was modified if you want to do that, that kind of thing, right? So yeah, there are many kind of approaches that different file systems have taken. I've listed a couple here of different examples. And then this image is basically another example of like a file system with a, let's not get into it too much, but if you're interested, we can talk about it after. Okay, but yeah, really drilling down into this network file system. The idea is that it offers transparent access to files. And this is a distributed file system, meaning that basically it'll be like Google Drive. So if I have like some sort of interface, maybe I open up my file explorer and I upload a file, and then Daniel accesses the same file system on his computer, he would be able to see the file, download it, whatever. And then also in terms of the implementation, which is the key thing, sometimes the files can be distributed across multiple nodes. So that this means either distributing parts of the files or basically distributing the files in a redundant manner. Those are both possibilities. Okay. Yep. I should take off the animations here, but just quickly walking through how one might edit a file using NFS. Basically, the key here again is that we're using remote procedure calls to access those files. So from the perspective of a user, it looks like all the files are locally on my computer. So if I want to edit a file, I would basically make some sort of system call to open the file. And then this would basically make a remote procedure call to the network kind of client stub. So just looking at this here, where I made my open call, like, hey, I want to read this file. This is kind of abstracting it through the virtual file system, and then through the network file system, client. And then this is actually making the call, the network call, to say like, hey, I need to read this file, where like to whatever server actually stores the files. And then the server here basically receives the request, and then kind of feeds it up to where we implemented like the actual code to do the read. And then it basically does the read and then feeds back through. And normally the client will cache a local copy of the file. And there's kind of some like nitty-gritty details in terms of like, oh, was it modified like at the server? Was it modified locally? Like when do we have to kind of push it out to the server so that other users can read the correct version of the file? So there's some details there that have to be considered. But the overview is that basically we're making use of these remote procedure calls to access a file on a different node. Okay, so this is the code again if you want. Any questions on that? I know I went pretty quickly. Yep.
Would it be more efficient to have the function implementation on the client machine other than on the server?
So the tricky part there is that the file is on the server, right? So you could probably theoretically it may be possible to move some of that to the client. But most of the time, the only operation this is really doing is like the open file, like get the file contents, right? And just like that part you can't really move from the server because the file is on the server. Okay, great. Yeah, you want?
Yeah, so before we start split everyone into groups, does anyone have like their own project data they want to pitch, or is everyone good with the set like distributed file system project? Okay. Yeah, this was just yeah.
Okay, so the idea here is that this left one is for the mailing list. If you haven't joined it and you want to stay up to date, definitely scan that. The right one here is the project like proposal form, which is a sign up form now. So yeah, our intention from the project, correct me if I'm wrong, is that basically you guys can form groups of 4-ish, or as many people as you're comfortable with, to basically work on this project. Daniel and I are going to kind of give you the code, kind of walk you through it a little bit, and then kind of be around here to give you pointers, like give you deliverables, that kind of thing. If you're not sure what to do. But yeah, so this form here is to fill out if you are trying to form a team.
Yeah, like only like a couple people filled out the form, so I was thinking just like
directly, right?
yeah.
Here? Okay, we can do that. Are you guys comfortable with that? If we just like divide you like physically here into teams?
Yeah. Yeah, I think that's the end.
But yeah, don't worry about the form. If you want it, you can. You have to
How do we do this?
So yeah, everyone just try to form a group of like 4-ish people, the people around you. We're just gonna come around, make sure that like your team is good, and then get the names and that kind of thing.
So like that's one thing where they have like their own channel.
I think that's a good idea. You just go to each team, get the names, and be created. Okay, this father part of it.